Hi, welcome to this video on operating modes. Now, in the last lecture, you may remember that we talked about symmetric key cryptography. And in the last part of that lecture, we talked about block ciphers. Now, I want you to recall that a block cipher takes a fixed sized piece of data and encrypts it using a fixed size key. So if we have AES here as our block cipher, then we take a 128-bit chunk of data, a 256-bit key, and when we put those together, we end up with a 128-bit piece of ciphertext. Now, it's important to note that a block cipher can only encrypt blocks of data. And in this case, the block size for AES is 128 bits. So it can only encrypt data in 128-bit blocks, not smaller, not bigger, exactly 128 bits. Well, what if I want to encrypt a larger message? So what if I have more than one block, for example? So if I'm using AES with a 128-bit block size, that would be 16 bytes. What if I want to encrypt something like a 30 megabyte video? Well, there's more than one block in a 30 megabyte video. In fact, there's a whole lot more. So what do I need to do in order to make that happen, since my block cipher can only encrypt one block at a time? In order to solve this problem, the fairly straightforward approach, and hopefully you're thinking of this, is we could just break up the big chunk of data into blocks that are the right size and just encrypt each of those blocks. Now, the way that we encrypt the blocks after we've broken them up impacts security of the underlying ciphertext when we're done. There are 5 traditional ways that we encrypt this set of blocks of data, and we call them operating modes because they're the ways that we use the block cipher in order to encrypt a large chunk of data. We're going to cover 3 of the 5 traditional ways in this lecture. And I just want to note that there are more than even the traditional 5. There are others as well. So the first method is called electronic codebook. And this is kind of the obvious method, the first thing that everybody comes up with when they think, well, how can I break it into blocks and encrypt it? In electronic codebook, you break the data into blocks, you encrypt each block independently, and then you use the same key for every block. So let's look at a diagram of this. So this diagram, which I have shamelessly taken from Wikipedia, because it's good. Wikipedia has excellent entries on operating modes, actually. I'll provide you the link later on in this lecture. So we simply take our plain text data, which is up here at the top, and we break it into blocks that are the right size for use with my block cipher. So if I was using AES, for example, then each of these blocks would be 128 bits. So I break it into these 128-bit blocks, and then I just encrypt each block with whatever key I'm going to use for the encryption. I get blocks of ciphertext. And then I take each of these blocks of ciphertext and I put them all together, and that becomes the ciphertext for my encrypted, say, video file. And I send that along. Now, decryption of this is just doing the opposite, which is what you would hopefully expect. You take the individual ciphertext blocks, you decrypt them using the key, and you get back the original plaintext, which you then put back together in order to get the original file. So ECB is the straightforward, simple approach, but it has some problems. The main issue is that the same plaintext blocks produce the same ciphertext blocks when you're using the same key. So if you have 2 blocks in the file that have the exact same plaintext, they're also going to have the exact same ciphertext. Now, originally we talked about a simple cipher, the substitution cipher, that had the same issue. Whenever you encrypt the same letter, if the same letter is encrypted twice in the same message using a substitution cipher, each time it becomes the same ciphertext letter. And this allowed people to perform frequency analysis attacks against a substitution cipher. Well, people can do the same thing against an ECB cipher. It's just a different idea because we're dealing with bits and entire pieces of computer files instead of just individual letters. But many computer files or other things you might want to encrypt on a computer already have duplicate blocks. By default, it's just normal that they would have duplicate blocks. And we don't want an attacker to be able to tell this by looking at the ciphertext. So we wouldn't want an attacker to be able to analyze an encrypted file and be able to tell you which blocks are the same, because that information could help the attacker figure out something about the original unencrypted version. And so we don't like this idea. So to illustrate this, so here's an example of a picture of a penguin. And if you encrypt that with ECB, and then you just display the encrypted data as if it were an image, you get this. And now if you look at that, you should pause and say, that's kind of disturbing. The encrypted image shouldn't look like the original one, but this one kind of does. Now, of course, it's not as detailed, but no, it still kind of looks the same. So you look here and you can kind of see that the white background here became this pattern here, and it's consistent throughout wherever the white is. And the black part of the body became some consistent pattern or color here. And the yellow on the feet became, again, a consistent pattern or color here. So because of the fact that in an image file we have a lot of repeated blocks of data, such as color, every time we see the color white, it's going to be represented the same way in the image file. When that white is encrypted, it becomes the same thing every time over here. So we end up with, just by looking at the encrypted data as if it were an image, you can see what the original image really was. And that's a problem with the encryption. So an improved approach, something better than ECB, is called cipher block chaining, or CBC. In cipher block chaining, each block is dependent on the previous one. And this fixes a lot of the problems with ECB. So let's look at what I mean by each block is dependent on the previous one. Let's start with the middle here instead of the beginning. So if I have a piece of plain text, in CBC what I do is that before I encrypt it, I exclusive OR it with the ciphertext of the previous block. So I take the ciphertext of the previous block, I exclusive OR that with the plain text of the current block, and then I encrypt that to produce my ciphertext. And what this does is this means that my plain text is mixed in with the previous ciphertext, so that even if two plain text blocks are identical, when they get encrypted with CBC, they're mixed in with something else before the encryption, so they don't result in identical ciphertexts. So even if this plain text and this plain text are identical, even if they were the same, they would result in different ciphertexts, because what was encrypted was mixed in with the previous ciphertext. It wasn't just encrypting the plain text data. So this solves that problem. Now, one thing I want to point out on here is that the very first block of data that you're encrypting needs what's called an initialization vector, because it doesn't have a previous ciphertext block. Let's take a look at that. An initialization vector is put in place because the ciphertext of each block is dependent on the previous block, and the first block has no previous block. It's the first block of data. There's nothing that came before it, so you can't exclusive OR it with the previous ciphertext. There is no previous ciphertext. So we pick a random value. We call it the initialization vector, and we use that as if it were the previous ciphertext block. So that's just what the initialization vector is. It's just a randomly chosen value. It's not even a secret. It's just randomly chosen in order to add that additional bit of mixing into the first block that you encrypt. So what does decryption look like for CBC? Well, in decryption, it operates kind of like you would expect. We're just doing the reverse of what the encryption was. So in decryption, we take the ciphertext that we have, we decrypt it, but that doesn't result in the original plaintext. That results in a value that's the original plaintext exclusive ORed with the previous ciphertext, because that's what was encrypted before. So in order to recover the original plaintext, we have to take that value and exclusive OR it with the previous ciphertext, which we happen to have because we have all the ciphertext. And that allows us to get the plaintext. So we're simply reversing the procedure that we used to encrypt with CBC, which now means that we exclusive OR with the previous ciphertext after the decryption. And again, for the first block, we have that initial vector. And in this case, when you're doing decryption, the initial vector is not a random value. It's the value that was used during the encryption. But since it's not a secret, that value can be shared freely. I can encrypt, choose a random initial vector to start with, and I can send you my ciphertext and the initial vector I used, and it doesn't change the security of the problem as long as the key remains a secret between you and me. So the initial vector is not a secret. So CBC obviously has this big improvement over ECB, which is that it doesn't have this one-to-one plaintext to ciphertext mapping. So remember our picture of the penguin, and when we encrypted it with ECB, we ended up with this picture that kind of looks still like a penguin. But when you encrypt it with CBC, we end up with something that just looks like static. Now, I'm not trying to say that representing ciphertext as a picture and it looking random somehow means that it really is, but hopefully you can see that this does eliminate that one-to-one plaintext ciphertext mapping problem. That's all these images are meant to illustrate. But CBC also has its own problems. The biggest one is that if I want to change the plain text of one block, I have to re-encrypt every following block because it's a chain, right? The following block is dependent on the ciphertext of the previous block, which is dependent on the ciphertext of the block before that, which is dependent on the ciphertext of the block before that. So we end up with this big chain. So if I'm going to change one plaintext block, I end up needing to re-encrypt every block that follows it in the file. Well, that's bad. If I'm doing something like a large encrypted file system or even a large encrypted file where someone might want to change just a few bytes on the inside, that makes the operation really slow because even if they only change 1 byte inside of the file or on the file system, you have to re-encrypt everything that follows. And that would be not wise for certain applications. But in other cases, it doesn't matter. If I'm encrypting network packets or something like that, it doesn't matter about changing 1 byte because bytes are not frequently changed in those scenarios. But in some scenarios, this could be a bad problem. So another type of operating mode, and the third one we're going to talk about today, is called counter mode. Now, counter mode is an operating mode that uses a block cipher to simulate a stream cipher. Now, you may remember that a stream cipher just generates a pseudo-random string of bits and then exclusive ORs that with the ciphertext, with the plain text. In counter mode, each block is encrypted independently, but it involves an incrementing nonce. And we'll look at that in just a second. A nonce is just a number that's chosen randomly, but it's not a secret. Just like the initial vector, it's not a secret. In fact, a nonce and initial vector are effectively identical in terms of what we're doing, but we give them a different name just because of how they're used. The initial vector is called an initial vector because it's the initial block used during CBC. But a nonce is used because that's traditionally the word for a random value used in an encryption operation. So anyway, let's look at our diagram here. So in this case, we take our random value, our nonce, and we append a counter to it. And then we encrypt that random value using our key. We just encrypt the value, and that produces some sort of bit stream, right? It produces a set of bits. And those bits are effectively random. And we take those bits and we exclusive OR them with the plain text in order to get the ciphertext for the first block. We do the same thing for the second block, except now we've incremented our counter. When we increment the counter, that means that we should get, on the output of the encryption, a totally new set of bits, ones that are substantially changed compared to the previous ones. So even though my plain text is only changing by potentially 1 bit, my ciphertext on the output of the encryption changes significantly. So I take those bits and I exclusive OR them with the plain text, and I get more ciphertext. So it's important to note here that unlike the other operating modes we looked at, in this case, the block cipher is not being used to encrypt the plain text. The block cipher is being used to generate a stream of bits that's exclusive OR'd with the plain text. That's a very important distinction. Well, in this case, decryption then just involves producing the same set of bits and exclusive ORing it with the ciphertext, just like we would do with a stream cipher. You encrypt by exclusive ORing with the bit stream, and you decrypt by exclusive ORing with that same bit stream. So in this case, our goal is to produce the same bit stream as before. And that means that when we're using the block cipher, we're still using it in encryption mode because we're just trying to produce the same bit stream we did when we had counter mode encryption. So with decryption, we're still going to use the encryption mode of the block cipher because, again, we're not encrypting or decrypting the plain text with the block cipher. We're just using it to generate that stream of bits. So operating modes are one of those topics that the first time you're exposed to them, they're difficult to think about and reason about. But if you spend more time reading and thinking about them, then they kind of become second nature and they become more obvious for you and easier to understand. So what I encourage you to do is to go spend more time with them by reading the Wikipedia entry on block cipher modes of operation. It's a really, really, really good entry. Apparently cryptographers love Wikipedia and spend a lot of time on there making it strong. So the Wikipedia entry for these is very good. So I would say go to Wikipedia, look for block cipher mode of operation, and you can find an excellent page that describes the 5 general modes and a few more, but gives their pluses and minuses and give you more information about them. And I'll add, just as a side note, if you're ever building something and you need an operating mode, chances are really high that CBC is what you want to use. The other 2 modes are useful for specific types of scenarios, ECB and counter, but CBC is in general useful for most scenarios that people operate under. So let's summarize. When using block ciphers to encrypt data larger than 1 block, you need to pick an operating mode. And your choice of operating mode impacts security, performance, etc. So you have to be able to understand how they work and to think about and reason about them. So hopefully this lecture gives you a good introduction to that. Thanks.